Uh, Good morning.
Buenos dias.
Buenos días. How are you?
Very good. And you, I was looking at your, it looks very interesting. I'm looking forward to it. What you
Now,
present.
Yes, thank you for sending the draft. From your comment, you implied that you were still working on it, Jesus. Do you have an update from what you sent yesterday?
yes, but not too much. I was only working in the at the end part in observer field, and I have some new version there, but not too much. Then maybe after the session, I sent to you this new version. Mhm.
Okay, great.
But I need to finish this paper soon because I have a deadline the next Friday. Then I have to finish it. This. I think that in the actual version, I have the complete panorama of the paper. Maybe I need only to add some conclusions, but it is the principal idea of the work there now. Mhm.
Okay, great. I don't, I didn't get any emails from Brian, so I suppose that he will join us later.
Maybe, yes. Mhm.
Yeah, we could wait a few minutes just to see whether he shows up.
Yes, or we can start when you uh, uh, decide.
Okay.
Okay.
Let me just ask you a few questions about the meeting that for which you're preparing this paper. This was a meeting in Panama, I think.
This is, excuse me?
The meeting that you're attending and where you're submitting or presenting this paper. I don't know very much about it, but I do recall that you said that it was hosted at least in part by Santilli, Dr. Santilli.
Professor Santilli sent to me an invitation for presenting our work.
Mhm.
And then he suggested that I presented the ideas around the interactions and formulation. But and I think that this is a good idea because I have to organize the proposal in an complete with a complete presentation of the principal ideas behind interaction problem. Then I thought that this was a good idea to send this paper
Yes.
to them.
It's an opportunity to the motivation to get something written, right?
Yes, yes, yes. Mhm.
It's,
Mm.
it's good. Uh, what is the main subject of that seminar or the meeting?
What I mean,
It's a very broad meeting. It has many different subjects. Centili is, I guess, the organizer of the particular session, which is related to now what
Oh,
he
okay.
was talking
So,
about. It's
so
pretty
it's just,
broad topics.
yeah, and spread in too much subjects. Yeah.
Well, I have a question. I was looking at your presentation, and in particular about the dual Grossman algebras that are so with respect to a vector space and the covector space, the dual Grossman algebras. Of course, that's exactly the ideas that I've been working on with this new type of local basis of null vectors. But so I'm very interested, particularly in that part of your paper there, that where you're talking about that and the references to that. I don't really know that many references.
Many of these ideas were worked with Professor Osiewicz in some early papers. I don't remember, maybe 2003, 2004. We were working in this. Some of the principal concepts that I am using were original ideas of Professor Osiewicz. Then the idea of the split of space in two complete sets of dual quantities are ideas of Professor Osiewicz, of course. And then I used that, but he were working in the idea of relative velocities. And then finally, he proposed the idea of groupoids, the category groupoids. But I wanted to think better in the problem of interaction, because it looks to me more fundamental. Then I was working with this, and then finally I think that hearing this paper have the principal ideas. Sorry, I need to open one door to my dog because it's making
no problem.
noise. Sorry.
So I think these ideas that Jesus is talking about is the same thing, what I call global duality. So the other bases that I'm looking at, I'm calling local duality, but global duality is exactly this dual Grossman algebras associated with vectors and covectors. And yes, I remember actually Vishakojevich's talk about these ideas back, I don't know how many years ago. I guess it was in the 90s sometime.
Thank you.
So the comment of, or the notion of interaction, in a sense, goes beyond, in some sense, what Zbigniew was talking about. He tended to focus on kinetics, right? Just on the motions alone, whereas when you start to talk about interaction, you are in a different subject, well, in a larger subject of dynamics in general. Right?
Yeah.
And
I'm still stuck on the idea of a global basis, which is the same thing as vectors and covectors extended to Grossman algebras, and what I'm calling now a local basis. So I'm just working basically with linear algebra, I suppose you can say. But
the point I guess I was sort of slowly getting to was that this notion of duality in the context of a dynamic situation so necessarily implies the kind of metric that you're dealing with, Dr. Sobchak, like where you sort of take it as fundamental that there is a kind of underlying Lorentzian metric, right, which necessarily implies that the duality involves a sort of a distinction between sort of something that is sort of time-like and another part of it which is space-like, so that it's like when you say time-like, you're referring to one part of the metric, and space-like is the other part of the metric. But that kind of duality seems, well, I'm not sure whether to consider such dualities as being fundamentally different than the sort of underlying duality in linear algebra. It's a little bit.
Yeah, I think that what I'm calling global duality is just related to Clifford algebra. It's the mother Clifford algebra, but local reality are the Lorentz geometric algebras of signature 1n. So, but yeah, it'll be interesting to hear what Hayes has applied this idea of global duality to interactions. And that's, I think, what he's going to be talking about using category theory.
Yes, I try to use the concept of duality from category theory. And I found some comments of MacLean around the relation of this concept of duality related with the problem of the adjunction. Then he says that in fact in the time he works, he writes his book. He says that the work was interrupted by the World War II. Then the problem was not finished. And he says that maybe the idea, for example, on Hilbert space are one important weight for working in this, because there we have the evaluation concept related with two quantities that are one covariant and contravariant quantities that gives to us one process of evaluations that is more precise is correct, the word, excuse me, more precisely. And then he says that the problems have not been solved, in fact, and then says only that the young researchers can work with new ideas and more fundamental ideas around this. But I think that the concept of duality is based in this principle. And when Professor Osiewicz proposed the duality concept starting from evaluations, I think that is a very interesting and good approach for the problem. I remember this is not written in the paper, but he said that evaluation can be considered like the power series of one set into the other. And then one can think in this like a functor that is taken to us from one category to the power series of, and that is another category. Then this can be reformulated using the opposite category. I'm going to use letters. If we say that A and B are categories, then one functor from the A category to the B category is the power the power of A category to the B category. And then this is a covariant functor. But one can seize this evaluation in a different way using the opposite category, that is from B to A. And then the power of this relation is B to the A, that is contravariant. Is a contravariant functor. And then when we consider both, then we have a kind of contraction between the two functors that give to us the evaluation. Then I think that this idea is very interesting for understanding the duality concept in a better way. Mm-hmm.
Okay.
Well, I'm just wondering whether the ideas of global or local duality could be translated into something similar. No. It's just a different concept of duality, but go ahead. I'm interested in what you have, what your talk will be now.
Yes. So I guess Brian hasn't arrived. So if you would like to sort of formally begin, although we've been already jumping right in, but let's you share your screen, Jesus, and we can.
Oh, okay. I am going to share. Mm-hmm. Mm. I don't know if you can see.
Yes, that looks good to me.
That looks good to me too.
Okay, here is only the abstract that sure you couldn't read, and how in another presentation I said I am trying to use the concept of F algebra for describe the states of one of a body, and using this concept of equilibrium state, I try to build the interaction concept between two bodies or more. First, I present in the introduction some preliminary ideas about the interaction concept, more historical than formal. But I think that in the first ideas presented here are the principal basis for the concept that I am presenting now. First of all, the works of Newton and Leibniz are too much important in the concept of interaction. I think that Newton basically introduced the concept of interaction through the concept of force, and with this he relate this concept with the concept of change of motions that are the fundamental concepts for the for his theory of mechanics. It is important to say it here. It is not presented here, but it is an important point that Newton make difference between different kind of forces that need, I think we need to explore more, because he speak about forces related with intensity that are producing directly change of in the state of motion. But he speak and devote several pages to the discussion around the concept of central forces, and I think that he tried to present this thinking that this kind of force needs to be wielded in different bases than the intensity forces. I think that this is an hypothesis that I am working, but I think that he thinks that the intensity forces are vectors and central forces are b-vectors. He don't knows this kind of concepts about the vector algebras, but I think that there one can find this kind of different treatment about the concept of force.
Jesus,
Yeah.
like, is that related perhaps to the sort of association of velocity with vectors, but rotation with bivectors, like, so that rotation is something that you can discuss in the context of a single body, but in order to talk about velocities, we would need at least the context of two bodies. Is that similar?
Yes, this is similar, but I think that the intensity forces permit to us and Newton to build the concept of one-dimensional space. And then when he speak about central forces, he needs he go directly to the to study the motion of the bodies in out of one-dimensional space. And then I think that this is too much important because he don't take too much time for discuss this, but the idea of that velocity is not parallel to the position vector is here fundamental because this is a product of the vector natural vector property of the central forces. Then I prefer to see this problem in this way, thinking even about the properties of the intensity, about the interaction, and then building in this way the properties of the space. Then this is the idea here. And Leibniz in almost up parallel way discuss the problem of interaction, introducing his ideas about vis viva and vis I don't remember how he says vis that, and then he built the concept of interaction like like an addition of these two principal concepts that are after called the energy of the system, the mechanical energy of the system. Okay, then I present this idea first, and I wanted to speak here about Truesdell because he present in his book a systematic theory about continuum mapping, and then he start defining formally several concepts that are used in his theory. In this way, it's too much similar to the work of Newton, but he works here with distributed properties that are fundamental in continuum in medium mechanics. And then he started with the formalization of the problem using two principal laws for his presentation that are the classical conservation of mass and the Euler's laws of motion. And then he developed his presentation of continuum mechanics in this way. I think that these two equations are fundamental because in the ideas that I am working here, we are continuum working with two ideas, properties of matter and interaction field. And these two equations, two fundamental equations used here by Truesdell, are related with the classical concept of mass and the law of mass conservation, and the equation of motion written in terms of Euler's equation. Then I think that these two ideas are complementary, and one is related with the property of matter that is called mass, and the property of interaction field that are the velocity field in the continuum. Okay, and these two ideas are related with the presentation of Franzen that are work devoted to present the problem of abstract data types, and he used the concepts of measurement, like the way of obtaining values related to the properties of the systems, and then after he relates this data with the principal with the measurement process, and with this he present a categorical theory about the measurement process, where he made a differentiation between the concept of intensive and extensive variables that he calls transvariables and intervariables. Transvariables are related with extensive properties, and intervariables are related with intensity properties. this is the principal ideas presented by Franksen, and maybe of this idea I am using in the development of my work. Another important contribution is from William Laver, that he works around the categories of space and quantity. In the same, in a similar idea that Franksen, Laver's present his work in terms of two dual kind of categories that are the category of the space and quantity. I think that he understands here space like space-time, and quantity like the process of get information about that space-time. And then he used category theory for presented this relation space against quantity, and he used described this relation using functors and natural transformation in this. In fact, many of these concepts are similar, because I think that he is using some ideas similar to the category of modules that are used in this work. But I don't remember the name of the category that he used in his in his presentation. I have not here in my text, but he used an special case of category that is related with the idea of model, the categorical idea of model. And then I need to add this here, because it is important, the name of this category that Laver is using. And here again, I like it to work in a different way, because I don't like to start with the concept of space in like a fundamental concept that is required for build the interaction concept. And finally, I cited here some of the principal works that Professor Siewek and I were working in, principally applied to the problems of observer fields for electromagnetism. Here, maybe is too much important, because some of the principal concepts are present here. For example, the idea of two fundamental laws that are one related with the properties of matter. Here is the charge current conservation, and another related with the electromagnetic field potential. And these two laws are the necessary laws that we use it for describe the electromagnetic phenomenon. Another important concept here is how the one can propose some absolute laws related with these two that are considered like laws of nature. Then this is important because we here there is an differentiation between the fundamental laws and the laws related with one observer. And then this take to us to the problem of observer fields that are related, and they have a different construction of this law, but they are only different presentation of the fundamental laws of nature. Then this is the principal ideas about interactions that are preliminary ideas that I have used for building the concepts in this work. Okay. Then here are the principal ideas of around interaction. I try to build here a formal definition. And then I started with the definition of algebra, like a triplet that is wielded with a ring, a field, and a morphism. And then these morphisms take the field to the center of the ring. Then with this kind of constructions, we can think that this algebra have this important property. This important property that is based for the building of a tensor product in like a part of his the principal operations that are used in this algebra. Then here is the first ideas. We start with sets of scalar fields that are part that are bodies in a category phi c that are bodies in equilibrium state. This is the presentation of a category. Sometimes I use it phi c for emphasize that we are in a category, but sometimes I not use that letter and only add an index to differentiate two categories. Then in this figure, you can see two different categories that are related with a functor, I-O-1. And this functor is a morphism that that apply over the one element of this ring, and then it takes to another category in this way. Here we have the morphisms applied to the element to one object or in the first category. Maybe in the notation that I have here, if we call A an element of phi 1, then sigma A takes to us to to one element in the category phi O through the morphism sigma. And then in this way, this morphism is a functor that is a relation between two categories. Between two categories. Here below are a more detailed discussion about this kind of relations that are used a functor. Okay, and then okay, here there's an important remark, because we can speak first. Sorry, I need to talk first about the about the addition operation here. Addition operation is used for represent the action of different kinds of interaction. Then if we have, for example, one electromagnetic interaction and an gravitational interaction, then we have two kinds of functors related to them, and the total interaction is the addition of this. Then this operation of addition is important, because this is used later for build a set of additive functors that we use for represent this interaction. Another operation is the composition. Composition is used when we have a sequence of different interactions, all of the same type. All interactions are of the same type, and then we speak around this, thinking like a composition operation. Then we have to here two operations that are addition and composition. And then with this, we get a functor that is represented this kind of operation, but is an additive functor. I think that later it is presented more formally. And then with these two kind of operation, we can take an universal construction for represent this kind of interaction, and these universal constructions have this property. In fact, we are having a build process where we are transforming one endofunctor in the category to another, and endomorphisms in the category to endomorphisms in another category. Then here we have in the right the category of the external body, and here we have the process in the category of the internal body. Then this is important because here we have the basis of how we can relate these endomorphisms with the property changes in the external category. And this is a fundamental process for the process of measurement here in the internal category. In this sequence, maybe it's better to use the all category and one category for differentiate those. And okay, here is only a remark taken in the properties presented in the commutative diagram. Okay. Okay, and here is the definition of interaction. Interaction is the action of phi 1 on phi naught and the endofunctor here in the category phi naught. And then we can speak about one reaction of phi naught to the phi 1 using an interaction too, but it is important to note here that we are in opposite categories in this two, and then we are relating these two opposite categories through the concept of interaction. Okay, and
Yes.
yes,
Just for clarification, you talked about properties of material bodies, and then also the endomorphisms, and I'm sort of wondering, is it correct to think of an endomorphism as not this, the distinction isn't clear to me. Like, so if we talked about, say, bodies having some intrinsic properties, that's maybe a synonym for what you said, being internal, right? But
Intrinsic, you use. Okay.
But so the endomorphism somehow, I think what you said was the endomorphism represents this internal property in some kind of external way, right? Is that correct? Like, so that.
Yes, because maybe in the next figure is better to see this this question. First, here I speak about equilibrium between two different kinds of categories. In the upper part of this graph, I am speaking about the category phi j. And here we have different objects that are represented different sets of equilibrium states. And here in the below, I have the category phi I, again with different objects representing equilibrium states. And then I have here the system in equilibrium. And in this way, I can represent this in terms of the composition of interactions between these two categories, between these two equilibrium states in these two categories. And this operation necessary give to us to the identity. Okay. And then if we speak about an interaction process in a situation of out of equilibrium state, then maybe we can take, for example, this state. This state is an equilibrium state after of going from the phi naught to phi 1 I. This equilibrium is getted by this automorphism that we can I used the word before endomorphism. But here is an internal process in the category phi I. Then, because this change of equilibrium here, this produces an action to the body phi j that was in the state not. And because this action, that is an external action to find not, it is produced an internal process that gives to us to a new equilibrium state. This new equilibrium state then starts a new interaction to the body phi I, and then because this interaction, it is produced a change in the equilibrium state. When I am seeing this kind of process, I am speaking here about an internal process in the body. And then I used the word endomorphism. I'm not sure, Professor, and it is a question for you, if it is better to speak here about endomorphism or automorphism, or those are synonymous.
An automorphism is from the same group to itself, whereas an endomorphism maps between two groups or two vector spaces. Automorphism is a mapping to oneself.
Okay, thank you. Then I need to use automorphism. Yes, yes. Mm-hmm. Okay, thank you. But then these are automorphisms. Huh? All of these are automorphisms. And this automorphism is in the category phi I. And here, those are automorphisms in the category phi j. And this kind of interactions that, with the classification of Professor Garrett, are endomorphisms, because those are the same kind of category. And then those are, at the end, those are functors between these two kinds of categories. Then, and this property is presented here. Then we have an additive functors that are the action of one body into the another body.
Yeah, and automorphisms have inverses, whereas endomorphisms might not have an inverse.
Automorphism is a isomorphism, right? To itself.
Yeah.
Right. So that, and then, yeah, a good way to say it would be that an automorphism is an endomorphism, which is also an isomorphism.
Okay, that's good. That's right.
Okay,
So,
thanks.
And automorphism is something more specific than an endomorphism.
Yeah, that's right.
You haven't sort of used the word isomorphism anywhere here, Jesus, although I think you did say, maybe you used the word identity somewhere.
Identity?
Well, when you showed, maybe in a couple of graphs or diagrams previous to this, you were defining what you meant fundamentally by an interaction.
Yeah, here. for example.
Yes. So
Mhm.
this I0 there is that intended to be an identity? So it like
Yes,
the composition
this,
with respect to composition.
sorry?
Well, you said, well, maybe even in 2.3, you have
Okay.
E
2.3 here.
sub 0. E
Uh-huh.
sub 0 is that you said E sub 0 is the unit of phi 0.
Oh, okay, this is a unit. I think that this idea of units are represented later. When I speak about the observer, this is identified like things like um, 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 sorry, like an idempotent and the composition of the ring. It is identified with units. Maybe okay. I take your comment, Professor Pesh, here, and then your idea is that here I not are identities, and E O are units.
Like a one, a unit one, I suppose.
And yes, is one. Is one here. Maybe I can change the notation here to.
I would say that I0 was an automorphism and I01 was an endomorphism. That's the way I would interpret that. That's correct. I0 was that is an automorphism, whereas I01 between is an endomorphism then.
Because these are between these two categories. I see.
Endomorphism relates those two categories then? An endomorphism, I01 relates those categories, phi1 and phi0. Is that correct?
Yes, that's correct. Yes.
And
And
I0 relates itself, so I would call that an automorphism then. Or it could be an isomorphism, I suppose.
here is in the category phi not.
Okay.
And is related to objects in this category.
But I subscript 01 is a functor, right?
I01 is a functor. Yes.
Yeah. It's not a morphism in that category, in either of those categories.
No, it's not a morphism in either category. But
what's the difference between a morphism and an endomorphism?
An
What's the difference between a
endomorphism
morphism and an endomorphism?
Well, an endomorphism is something that maps to itself, but it's so. So I think it's correct to say that I0 is an endomorphism, but it could also be an isomorphism, in which case you would call it an automorphism. Too many morphisms.
okay, yeah, okay, but then here we had two kind of morphisms, one between two categories and one inside each category. And those are related through with no, both are necessary for define the interaction. Okay, and okay, here I am. I go to the concept of extensive and intensive properties. Here, the idea is related with the measurement process, and the principal ideas here is to distinguish between the properties that are related only with one morphism between these two categories, and the other are related with the process inside each category. Then, in principle, I am considering here that we have two bodies, and each body produce an interaction in this category. Then, because these two interactions, we can speak about a new body, understanding this like the Cartesian product of these two bodies. And this is called this new body is called V1 plus 2. And then we can, if we can speak about one process in this category produced by the two bodies, 1 and 2, then this is wielded by the Cartesian product of the separated bodies. And then in this way, we can say that we have an additive property. Then we speak here about an extensive property if we can get this for the representation of that property. This is the idea with the extensive properties. Of course, here in the process of measurement, in the process of measurement, one needs to think that the process of medition are the same for these two bodies, because maybe in general these two bodies can interact with different properties. Then we are speaking here about the same property, and then this is identified here by the process of measurement that that is used. And then in this way, one can think about extensive properties. And here I am speaking about intensive properties. Intensive properties are related only with the arriving process of this action of the body phi j. This is in fact represented with this morphism sigma that is in the figure 2.2. I go fast to this here in the way of identify here. In fact, I01 is related with this kind of morphisms, and then this is related with the process of measurement that we are using here, and this is related with the intensity of the action of phi j, and this is represented by sigma. Okay. And then here I present algebra, a categorical algebra for the interaction. First, we speak here about the composition rule that can be interpreted in different way. One of these is one of these consider the action of phi 1 on phi naught via I01, but followed by the equilibrium process here. And then after the equilibrium process, a measurement of the interaction is taken, and then a reaction is started that takes to phi 1 to a new equilibrium process. Another way is to think about one action in phi O that try to perturb the body phi 1, and then he start a change of equilibrium process here, and then start this action in body phi 1, and then this action takes to body phi 1 to a new equilibrium process that answer with a new interaction. This is, for example, like a kind of perturbation that we made in an external body in the way of we can understand the properties of that body. Then this can be summarized here in this kind of homomorphism that are the onsets of the category. These onsets are related two kind of bodies. The change of a state in in body 1 and the tensor product of the action and the change of a state in I naught. Then we have here these two relations. First, seeing the action in sorry, I think I have here an error in the expressions. No, okay, this is okay because we have here. Sorry, I lost the comma here, and then I thought that I have an error in this equation, but not. Then again, I have the change of a state in phi 1 and the action on phi naught. And here I have the change of a state in phi 1 followed by the action, and then the change of a state in phi naught. Then this is related with this different kind of interpretation that we can see in the figure before. And then with this property, we can speak here about an adjunction between these two categories through the functors I, J, I, and Ij. And then we have seen here this property that is based in the action of this triplet that is acting on the category phi I, and then this acts on the category phi j. Then we can illustrate this in this way, that are the action and reaction of this process that are giving to us this adjunction. Okay, and then okay. Here it is this relation is important because this phi is the relation between these two kind of interpretation in phi j, that we have here the from the home set phi j, here is expressed in terms of this interaction, and in this state of the body J. And here we have the home set in the body I expressed in terms of his state and the action of the body J. Like you can see here, we have not compositions, but the action of IID on the object phi I. Then, and here we have the action of the functor Ji on the body phi J. And then those are related by these bijections that are the basic idea in the process of measurement that we are using here. Then, okay, then we start here with the idea of server, and then we first select one particular object that the observer. This observer is taken in interaction with a system of objects, and then his measurement does each object via this process that we used before. Here, the lower index are related with this observer, and the upper index are related with the body that are interacting with psi O. Okay. Now I start here the properties of these measurements that made the observer psi O. First of all, we can say that this is an idempotent, because when if we take, for example, here the phi 1 acting on psi naught, then the action is produce an change of equilibrium in this observer psi O, and then again the same actions, then not change the state again, and then we have here an idempotent. This idempotent is a covariant functor because this take the state in the body psi O and to the change of to the change of state, and then sorry, I have here problems with this notation because I have to use it here psi and not phi. Because I am speaking here about the observer. Then I need to correct this because this is the observer. This is a process in the observer. Then this process is taken from one equilibrium state in the observer to a new equilibrium state. This equilibrium state is getting here by an internal process, and this is the same, but acting on the external action of the body phi 1 on the observer psi on, and this takes to us process where the action I not 1 is restricted to the equilibrium states related with the internal process in the observer.
So idempotents generally represent observers, then, is that correct?
Yes, idempotents here are, we can use here idempotents in two different ways. One of these is building a observer. And then this observer is built selecting an special IO. And then the state, the category psi naught is split into parts. One with one idempotent and one with the complementary idempotent. Then this is the idea, and one is the kernel of this idempotent, and the other part is the image of this idempotent. This is the idea here with the observer, and then and here there is the other idea, but sorry, I couldn't finish this. But the idea here is that if we take the psi naught, then this psi naught can be split in with a set of idempotents in the way that each idempotent gives to us one ideal of this phi. And then in this way, we are getting a complete representation of this psi in terms of idempotents, and then we have a set of idempotents related with scalar fields that are representing the state of the system. This is neither more development here.
So idempotents project onto steady states, then, I would suppose, which are represented by observers, then, if I understand correctly.
Yes, because here I have using two ideas, and First, I am taking here this idea, this principal idea. These two are idempotents, and these two are complementaries. No? That is, if we can split the category psi not in terms of these two idempotents. And with this idea, one can define an observer, because here we have, for example, defined here time and space. And with this split, one can describe all the system.
Yeah, maybe a principal idempotent represents an observer because,
Yes, a principal idempotent. Yes.
That's an observer.
Yes, this is representing an observer. But another way of doing that is to split the category psi not in terms of a set of idempotents. In the way that we have here a complete set of idempotents. Then with this, sorry?
Mutually annihilating idempotents. If you multiply one times the other, I10 times I20 is equal to 0. They're mutually annihilating.
Yes, those are orthogonal idempotents.
Exactly.
Yes. And then, okay, then I can build the category psi not in terms of these idempotents. But this is not observer, but observer is this splitting that we are using here. This second splitting is the totality of process required for describing one object, one external object. And then we have here for one way and the properties of matter and interaction fields. Then with this we are splitting the category using ideals, and with each ideal I am relating one unit. And here Professor Pech is where so your comment before about relate I/O with units, because those are units, and then I'm split it here in terms of interaction fields are like a block decomposition. Then the idea is finish this idea with this block decomposition. Maybe this graph is needed to move it before, because it is related with the definition of observer. That is that I put it here before this. Mhm. Then after of this, I need to put these graphics, because here is that splitting that I am presenting in the question before. Mhm.
Yeah, it's probably a good idea if that diagram was a bit earlier in your paper. It sort of presents the physical justification for your formalism.
You suggest that I have to present before?
Just that the especially the use of these terms, the like recurring process
Okay.
and time,
Yeah.
because earlier in your paper it's the same sort of diagram is presented, but it's more abstract, and so it's perhaps harder to understand why you are defining things the way you are.
Yeah. Well, okay. Thank you. I am trying to move it before, but I don't know if I can move it before these ideas of okay, maybe
or maybe just to
maybe
make a
here.
yeah, or maybe in this area, if you referred to the section below for more
Oh,
how should I say,
okay.
for justification of the
Yeah.
formalism.
Okay, because I hear I am presenting here extensive and intensive properties are maybe, but I need the idea of splitting. Okay. Oh, okay, I am trying to move it before how you suggest, because I think that it can be useful for the rest of the presentation. Mhm.
Now, just one other comment. You're using idempotents extensively, but you've never mentioned a nilpotent. Does nilpotence arise in this particular way of looking at things?
Yes, but these nilpotents are used in the building process of this kind of sorry, maybe here in this part, when I am speaking about one implementation, and I need to speak here about this decomposition of a differential form, then I need to use internal and external product, and I need to use idempotence and nilpotence for working in this algebra.
Yeah, I would say that nilpotents are really more fundamental than idempotents, because you can construct all these idempotents from nilpotents, which is the interesting thing. That
Okay.
so if idempotents are a principle of idempotence, then what are nilpotents and what's the interpretation of the nilpotent in this way of looking at things?
Maybe here, when I wanted to speak about the Bloch theorem, I need to use the concept of nilpotents for this kind of decomposition of the category.
Well, that's very interesting. I find that very interesting ideas here.
Okay. Okay, but I am going to work in this idea that you are suggesting here. Mhm. And okay, this is the principal ideas of that I was working, and here I am only presenting some an implementation using Grassmann algebra. I am putting here some of these properties, and then with this I can I think that it is needed here to speak about observer here, but not necessarily because I am trying to work in the more general way about the implementation. And then at the end, I am only using some kind of differential forms for illustrate this. I only put this, but I have more examples with, for example, electromagnetic interaction, or continuum mechanics is another, or the work presented by David Perez in the Congress of Osievik Congress in the past 2 years ago about the equations of related with gravitational interaction. I don't remember the name, but those are a pair of equations that are similar to the equations that are used in electromagnetics and in continuum mechanics and so. Then I am going to include these examples here. Okay.
Okay. Well,
this is the
I think examples are very important. A very important part of your talk are the examples.
Okay, thank you very much.
All right. I think you've done a lot of work here on this, and it's challenging to present this material to your audience there in Panama. I think they probably would appreciate having some more concrete examples of. So it does seem like the physics seems seems more clear to me when you speak in terms of, say, light and light as a form of interaction between material bodies. It's perhaps otherwise the concept of interaction seems very abstract, and so without additional examples,
I think it helps very much to identify, for example, an observer with an idempotent and mutually orthogonal idempotence. As if you can work, I think those ideas, because they fit in right in with linear algebra, of course, immediately. And I've spent a lot of time with idempotence and nilpotence in my own work, so it sure makes it much clearer to me. The physical identifications I think are very important, and also all those examples that Professor Page or Dr. Page is talking about as well. Well, that's what the end of the talk, of course, was using electromagnetic ideas from electromagnetic fields.
Mm-hmm. Another thing that I still find really intriguing is the notion that a material body might have some intrinsic properties, that properties that exist independent of other bodies. But then when we consider interactions, we want the interactions not just to be a consequence of an observer describing the dynamics, but rather the interaction also has to be an intrinsic, like internal property of a set of bodies, and so that this, and I think that gets a little bit confused especially in the theory of relativity, like when something is an absolute and when it's something that's relative, and when the things that are relative start to interact with what we mean by dynamics, it can get very confusing. Like so, for example, just asking whether or not energy is a relative or an absolute concept, leads to a lot of confusion in relativistic dynamics. So if you can present the notion of interaction in a way that is absolute, that exists independent of an observer, and then introduce what you mean by observer later, like so that it's so that an observer is not an inherent part of the dynamics, I guess, is what is the view that was originally taken in relativity. But it's not the view, of course, that's taken in quantum mechanics.
Yeah, well, that's what I was going to mention. Can you give an example with quantum mechanics? Because idempotence and nilpotence, they're the basis of quantum mechanics as well. So can you tie it more directly to some ideas from quantum mechanics too? I think would be very interesting.
Yeah, but here I have some problems because I think that with the presentation that I am making, the idea of absolute laws are far from this presentation, because the relativity is intrinsic to the concept of observer. then yes, this is a problem because one side I am using the idea of Professor Siewicz that there are universal laws and there are observer laws. And then when I arrived to this idea, the concept of observer are a fundamental part of this presentation. And then the concept of fundamental law is too much difficult to present in this way. And then when I was arriving into this idea of the description of the system, but a block decomposition, then I am strongly relating this with the observer, because it's the observer that use the set of scalar fields, and then is the observer that decided how he can split this. And then I arrived to a different idea that Professor Siewicz was used to, that he said science is subjective.
So science would be
Science is subjective. It's subjective.
That's the observer laws. What was the other laws? Was observer laws and physical laws, or what was the other one?
Yes, but it's better to use observer laws and absolute laws. Absolute laws. Yes.
Oh, that's interesting.
And
when
then
when you say observer laws, I mean, that would be a synonym for relative, right?
Okay, yeah.
yes, yes. And then the ideas of subjective science is present in this in this way of presenting the concept of interaction.
So absolute laws would be the tie between the two, as you were saying, the interaction between the two, I suppose.
Yes, because interactions only have sense if we speak about an external body and an internal body. Yeah, and okay, but and then I think that there is a
I
kind.
understand much better now the ideas of Professor Ojevich. Many years I did not understand. We had a hard time communicating, but now I'm getting to understand through you some of his ideas that I could never understand when he explained it to me.
Yeah, and I think that one can speak about universal laws like an space, like a kind of consensus between observers. And then with that consensus between observers, then one can postulate the universal laws and then the unique that one can make is to check about the validity of this postulate. And then, okay, this is the principal ideas around this proposal. Okay.
I'm reminded of the work that Oshevich was doing on the notion of center of mass in relativity, right? Because this is a bit of a problem, because, for example, if you have say a system of bodies like the solar system with these bodies all interacting with each other, but then outside of the solar system we have an observer who's taking measurements of the solar system. So we would believe that the solar system has a dynamics that's independent of whether someone is taking measurements or not. I mean, so this sort of abstracts at least away from quantum mechanics, and we're not worried about quantum mechanics here, but we're just worried about describing the dynamics of the solar system, but from the perspective of a certain external observer, of an observer who's not part of the dynamics. And so it's disconcerting to see that in at least some formal versions of relativity that the notion of center of mass remains dependent on the observer, right? It's not something that is a property that we can deduce directly from the system of bodies constituting the solar system as a whole, but it's going to always depend on who's taking the measurements and the theory that observer creates. The theory is based on the observer's measurements, but that's a confusion of confusing the theory with the object that it's supposed to represent. Right?
Yeah, two bodies are moving. Two different observers will say the center of gravity is at different locations, I guess.
Mm-hmm.
So
yes, but this was a point that I discussed too much with Professor Osiewicz, because in my mind, if we speak about a center of mass, we have one more observer.
okay.
And the only way that we can have a center of mass is because there are an external observer to the two bodies.
Okay, that's interesting.
Or there exists the ether. Huh?
Yeah, in some absolute dynamical sense. Yes.
Yes. And then this is the problem with the center of mass.
We were coming back to this problem we always talked about very early after the idea of these why three observers are necessary. I can understand that better now.
Yes, for speak about center of mass of two bodies, we need one observer outside of these two bodies. Outside. Yes. But there are many.
That's strange, because if you have two observers outside the two bodies, then it becomes even more confusing.
Not too much, because I think that between two observers outside of the system, we need only one kind of conversation for interchange information. And then light here plays an important role here, because it's the way that they can interchange information. No?
Okay.
And then I think that there is not too much problem, because we need one compensation and one way of interchange information. And that.
Okay, well, maybe that's good for this session. I'm not sure if we have any particular agenda. We haven't really mentioned what we might speak about in 3 weeks' time. I know in our previous meeting, Dr. Sobczyk, you indicated you were continuing your work, and you did send us an updated draft, I guess. You presented, you actually posted.
Yeah, I am making some progress. I maybe in 3 weeks I can at least maybe half, and then maybe Professor Cruz could continue. Talk about his updated version. I'd like to tie some of these ideas together. I think this idea of local duality can be incorporated into these ideas you're talking about as well. It's just a different concept of duality, which involves only a single Grossman algebra, not two. Global reality involves two Grossman algebras, but local duality only involves one Grossman algebra. But it's still a concept of duality. And I think I can relate the two together much more clearly next time, at least, but not the whole time. But I would like to hear what you had to say, how you finish up your paper that you want to present in Panama.
Yes, I really like to present some of this. I confused that working in this organizing this paper has opened many problems and ideas around. Then I think that it could be interesting to speak about it.
Well, that's good.
Maybe that is a good approach too, is actually to summarize what those open problems might be. Like,
yes,
since this is evolving research.
Okay, yeah.
I really think that nilpotents are the most basic elements which you can build the idempotents out of, and that's what I'm working on. The relationship between the two concepts of duality, which I consider equally valid, really.
Just to be provocative, isn't that saying that Grassmann algebra is more fundamental than geometric algebra or Clifford algebra?
Well, Grossman algebra, that's right. Grossman algebra together with a metric, two Grossman algebras together with a metric give you the mother algebra of neutral signature, whereas a local duality gives you the Lorentz. On one geometric algebra gives you the local duality concept. So Grossman algebra is a basic. That's right. The nilpotents are nilpotents are built up. Grossman algebra is built up from nilpotents. So nilpotents are the basic idea fundamental to Grossman algebras. And then Clifford algebras arise with the notion of a metric, but that can come in just by the inner products of these nilpotents. That's where the idea of idempotents come from. Anyway, that's what I like to explain more clearly and say half the next time, and Jesus Cruz I think we can split it pretty nicely between us the time.
Yeah.
Yeah, I think that's. I'm almost getting convinced about what you're saying about local duality. Like, especially if you're saying that if we start with a single Grassmann algebra and then just add enough structure so that we can define what we mean by local, um, then if from that we can do all of Clifford algebra, I think
Well,
then
that's right. They're very closely related, really. It's just instead of Lorentz Clifford algebras, with two Grossman algebras, you get the usual structure, that duality structure that Professor Cruz is talking about. But you can do with just one Grossman algebra as well.
Mhm.
It defines a local duality relationship. So I can
that's-
relate those two pretty well next time, I believe.
Okay, all right. Well, let's plan on that. Say in 3 weeks' time, we'll talk a lot more about this local versus global duality. I think that's interesting. Okay.
All these ideas are really related now. I can see much more clearly what we're talking about.
Well, it's been a few years, well, like maybe almost as many as 2 years now that we've been talking about duality. So it's good to see that we haven't gone off in completely different directions. I guess that's.
The graph theory is a little on the side now, but there is deep relationships also between graph theory, but maybe that's more difficult really to tie it together. I don't know how Professor Cruz wants to use graph theory in his discussion now, what he's talking about, or whether he can use it with regard to category theory. Well, okay, we talked a little bit about the relationship with category theory. Well, an example being graph theory, but maybe there's more deeper ways of looking at it.
Okay, we'll talk more about it in 3 weeks. I hope everyone has a good. Well, you'll be having American Thanksgiving should be coming up somewhere in there, right? In that time.
Well, 3 weeks take us into November. Will be American Thanksgiving. I think is November 24th or something like that.
Oh, okay. I always get that confused since Canadians want to do it at a different time.
No, they're not. They're stopping. They're not using the word Thanksgiving anymore. They're calling it the Holocaust, Indian Holocaust.
Oh, yeah. Everything becomes political now.
But it is November 1, no?
What was that?
In 3 weeks, it's
Yeah. So that's
November 1.
November 1, is that when it is? Okay.
Yeah.
That's an important holiday in Mexico, isn't it?
Yes, but no problem.
What is the holiday in Mexico again?
Yeah, it's holiday in
Day of the
Mexico.
Dead.
In Mexico, it's
Oh,
holiday
Day of the Dead.
number
Okay.
1 and 2.
Muertos.
Muertos, Día de Muertos.
Yeah, Dia de Muertos. Okay.
Día de Muertos. Mhm.
Okay. Well, see you in 3 weeks then.
Okay.
Bye for now.
Professor Pesh, don't you have some subject you want to present?
I remain sort of undecided about that. But
Well, that would be just
personally,
three observers. If you can explain that better. I was trying to get you to do that earlier. Maybe with these ideas floating around, now we'll be able to finally get to that idea. That would be interesting, I think.
yes, perhaps. I still am focused mostly on my own research and with another colleague of mine on the subject of quantum mechanics. That is, looking at models of quantum mechanics that are how should I say that? Less more founded in classical mechanics, like in the sense of, for example, Nelson's ideas about stochastic mechanics as being the foundations for quantum mechanics. That is that we need we're looking at ways of deciding what is real in quantum mechanics. What is the underlying ontology, and trying to find an ontology that is acceptable. So it's still very much like the kind of subjects that Dr. Santilli was talking about, but with a different spin on the answer, right? Like by saying that that one possible understanding of quantum mechanics is as a statistical theory in which the population that you're describing statistically has its own dynamics. So this dynamic is sort of would be properly described as the relationship between worlds. So that we're not talking about the statistics of many independent worlds, but rather many interacting worlds. And this I don't know. See, I have trouble
with all these ideas put together. Really, somehow we just don't understand how.
Yeah, I certainly don't understand how to fit this notion of many world interacting dynamics, which is the kind of the foundations that I've been looking at in quantum mechanics. I don't quite understand how that can be given the same foundations as. But anyway, so it's sort of off the side of duality. I can't relate what I'm talking about to duality very well at this point. And so I certainly at some point in the future, I'd make another attempt to describe.
Well, maybe what you're lacking is local duality. So I can clarify
Perhaps,
that.
Well, that's every time you say that, every time you use the word quantum mechanics in your papers, Dr. Socek, I think, now is that what I need? Is that what I'm missing? So yeah, perhaps maybe we'll be able to have a better idea about that at next meeting.
Okay.
Okay. So
Great.
again, bye for now.
Okay, bye.